Hi everyone. Good morning, guys. Please confirm that am I audible to you or not? Hi, good morning, Shillong. Last time we got disconnected. First of all, tell me, guys, do you have any confusion or doubt? The topic that I was discussing in the last class. Hi, good morning, Itanagar. Guys, confirm once. Do you have any doubt from the previous class? Hi, good morning, Senapati. How are you? Critical phenomena. Okay. So I'll discuss, yeah, sure, I'll discuss about it, critical phenomena. I'll repeat that again. So guys, I'm repeating the critical phenomena, okay, that we were discussing in the last class, okay. So just look at your screen, try to understand. See. This is the container where gas particles are filled initially. Okay, only gas. This is your external pressure. So I am increasing the external pressure. What does it mean? That piston will move towards the bottom, and due to which the pressure inside will get increased. And I said, let's say suppose some gas particles is converted into the liquid, but some are not. Means there is a state of equilibrium where you have got the liquid as well as the gas. Okay, so we can say that here we have got gas as well as liquid. Okay, now we are further increasing the pressure, and we are increasing to such an extent where all the gas is converted into liquid. So finally we have got only liquid. Okay, so first of all tell me, are you clear with this one? That we are constantly increasing the pressure, and by increasing the pressure finally we have got a state where we won't have any gas molecules, we will only have the liquid particles over there. Are you clear with that? And obviously between conversion of gas into the liquid, a stage will be reached where we will have gas as well as liquid. Okay, let's continue. Shillong, due to the net issue, I cannot see you clearly, even your actions. So kindly use the chat, as well as the other centers like Itanagar and Senapati, guys. Please use the chat okay, to respond me. Okay, so let's start again. Let's start to the new point. See, now I'm plotting a graph. See, Boyle's law we have already studied. This is P versus V graph, which look like this. And this is only for the gas. So if we have only gas, we can have such curve. Okay. Now I'm plotting the same graph. See, I'm plotting the same graph for these processes. Look at this. At initial state, you will check out there is only gas. Okay. So first of all, I'll draw the gas. Remember, this is your pressure. As this, in this direction, pressure is increasing, and whereas in this direction, volume is increasing. Okay. So this is the curve. This curve represents only gas. Okay. Now, in the next state, we have got what? Gas as well as liquid. So if I plot that, it will look like this. Okay. Here, this red region represents the gas as well as liquid. Now, the third part, where we have got only liquid. Okay. So, liquid will be present at extremely high pressure. Okay. So, I can say that this looks like this. Okay. If I mark them as A, B, C, and D. So what can we say? The AB region represents only gas. The BC region represents gas as well as liquid. Whereas CD region represents only the liquid. First of all, confirm me. Are you clear with this one? Are you clear with this one? With this graph? Okay. Just tell me one thing. At the higher temperatures, what will you get? Liquid or gas? What will you get at the higher temperature? Liquid or gas? Yes, absolutely. Gas. So now look at this. See, this is liquid and gas region. So obviously this liquid and gas region will slowly start converting into the gas. Even this line as well will slowly start converting into the gas. Okay. So obviously there is a point reach if I constantly increase the temperature. See, this phenomena is taking place at a particular constant temperature. Okay. Now what I'm doing, I'm constantly increasing the temperature. So on constantly increasing the temperature, a point will reach where you will get exactly gases. And below that point, the conversion of gas into liquid will just begin over there. Guys, obviously there must be a certain point on increasing the temperature where we can get just liquid. And above which we won't get any liquid, we'll get only the gases. Okay. First of all, understand this point. I'm saying on increasing the temperature, we will have a point above which we won't get any liquid, but below which we can just get that liquid. Okay. So that point is known as what? Critical point. Okay. At that critical point, whatever temperature we will have will be known as what? Critical temperature. Whatever pressure is there will be known as what? Critical pressure. And whatever volume occupied by the gas particles, which is in the form of liquid, will be what? Critical volume over there. Okay. So just look at this graph. Look at this graph. I'm drawing it again. See, This was the initial state. Now what will slowly happen? This is, let's suppose, at T1 temperature. You are increasing the temperature. So what will happen? That this region, means solid and liquid and gas region, will slowly start shrinking. Okay. So I'll say at the next point we will get this one. This is, let's say, suppose at T2. This is at T3. This is at T4. This is T5. And now this is T6. Guys, look at this. Look at this. Slowly the nature of the curve is changing over there. Okay. Now I have marked a point. I have marked a point. This point is representing what? Critical point. And in terms of temperature, what can I say? It is the what? Critical temperature. Above which at T6 you can check out, this is actually the graph of Boyle's law. And graph of Boyle's law represents only what? Gases. Okay. So what can I conclude from here? If I compare T1, T2, T3, T4, T5, T6. So obviously T6 will be highest one. T5, T4, T3 and T1. Okay. And we can say that T5 is what? Critical temperature, which is represented by the Tc. Okay. So this is how the nature of graph will slowly get changing over there, and we will get a point where we will just get the liquid. That point will be known as what? Critical temperature over there. Confirm it, guys. Are you clear with this? If you have still got some doubt, you can please ask me. I can tell you some other example as well. Hi Tamilong, how are you? Test is a new word? Okay, yes. Okay. So guys, I hope so you have already copied this graph in the last class. Okay. Let's move on. Let's write few important definitions. And I think I have already told you that out of temperature and pressure, what is the important factor, guys, for the liquefaction of gas? Out of temperature and pressure, which is more important? Temperature or pressure for the liquefaction of a gas? Okay, very good, Tamilong. Yes, nice, Shillong. What about you, Senapati and Itanagar? What are your views? Would you like to comment something on this serious topic? Okay. Yes, temperature is the most important factor between these two. Okay. So guys, now let's write few important definition. Critical temperature, represented by the Tc. Guys, just copy with me. Okay, these are the important definitions. It is the maximum temperature above which gas cannot be liquefied. By applying any pressure but below which it can liquefy. It can be liquefied. Okay. The formula for this one is 8 by 27 A by RB. Copy. Then critical pressure, which is PC. It is the minimum pressure required to liquefy the gas. Formula for this one is PC is equals to A by 27B square. Next is critical volume, VC. Volume occupied by 1 mole of gas at critical temperature and critical pressure. And VC, which is critical volume, is equals to 3B. Copy, guys. Copy and then confirm. Okay. Guys, I'm giving you a question and you have to solve that question. Question is, for a gas, PC is 1.5 atm, TC is 320 Kelvin, predict in which of the following condition liquefaction will take place. First, pressure is 2 atm, temperature is 300 Kelvin. Number 2, pressure is 1 atm, temperature is 300 Kelvin. Pressure is 2 atm, temperature is 350 Kelvin. Number 4, pressure is 1.5 atm, temperature is 310 Kelvin. Pressure is 1.5 atm, temperature is 320 Kelvin. Do this, guys. Check out in which of the following liquefaction can be possible. Attempt and tell me your answer. Guys, have you done that? How many more days you need? 1, 2, 4. Okay. What about you, Temelong, Senapati, Itanagar? What's your answer? What do you think about it? So guys, first of all, let's mark the temperature because this is one of the important criteria. See, critical temperature is already 320. So we know that above 320, we can't liquefy any gas. So obviously, in case 3, the critical temperature is 320. Okay. So 350. So obviously, in this case, we can't liquefy it. Okay. Now, critical pressure is what? 1.5 atm. So check out the pressure where the pressure is above 1.5. In the case 3, it is it is above 1.5, even in case 1. Even in case 1. Okay. But in case 1, the condition of critical temperature is absolutely correct over there, and I have told you that critical pressure is not a very big criteria, but critical temperature is. So first can be the answer. Okay. Second is totally satisfied. Third is crossed. Fourth can also be done. Let's check about the fifth one. Guys, reread the statement of the critical temperature. It is saying above which we can't liquefy. Means at that critical temperature, we can liquefy. Reread the statement again. The statement was saying above which you can't liquefy. But yes, at that point you can liquefy. So tell me, should 5 be the correct answer or not? If you got confusion, please you can ask me. Sometimes it happens I'll say something very fast and okay. So yes, fifth should be the answer. Because this temperature is 320, which is equal to this one. If I write it 321, then we can't do this. Are you getting this? If I write the 321, then we can't do this. But yes, at that point we can do this. Okay? Got it? So answer would be what? 1, 2, 4, 5. Means almost all are the correct answer over there. Okay. Okay, so guys, finally, after lots of efforts, yes, Itanagar absolutely right. After lots of efforts, we have completed states of matter. Okay. That's all about the states of matter. We have finally winded up. Okay. So we have completed redox, mole concept, structure of atom, chemical bonding, states of matter. Okay. Now we are going to start with the equilibrium. Okay. So guys, you can clap for yourself that we have completed such a good task actually. Okay. So you can appreciate yourself. We have wound up with the states of matter. Now we are going to start with the equilibrium. Again, one of the most important and the quite interesting chapter. Only when you will study it along with me. Okay. Now guys, what's your work? I have already shared the previous year's questions of the NEET chapter wise. Pick out that PDF file, check the states of matter or the gaseous state chapter over there, and attempt all the questions, whatever is given over there. Is there anyone who has already started doing the questions from that book? Is there anyone who has already started? Okay, I cannot see your actions, guys, just because of the net issue. Okay, Annie has started. Very good, Annie. And guys, oh, nice, Balajit. So guys, those who, first of all, tell me, are you able to solve the questions? Or you're failing or facing some difficulties over there? Lima has started. Very good. Priyanka has started. Very good. Is Priyanka is in this class? Iba has already started. Oh, I think whole class has started almost. Okay. So guys, first of all, tell me, are you able to solve those questions quite easily, or you're facing difficulties over there while solving previous year's NEET questions? That's really good. That's really good. Whenever you stuck over there, ask each other, help each other. Okay, post your questions on the group. Okay, and yes, we will have doubt sessions as well of every chapter. Okay. Yes, we have planned doubt session of structure of atom as well, but unfortunately we can't do this today. Reason being, first of all, that I have forgot the booklet at the home. Okay. And second thing, I have to start with the equilibrium. Okay. So I'm giving you the new date for the doubts of the structure of atom. That will be in the next week, whatever first class of chemistry will be there, whether it is on Monday, Tuesday, Wednesday, on any of the day in the next week, you will have doubt class of the assignment that I have shared with you on the group of the structure of atom. We will have doubts of that chapter over there. Okay. And after that, we will have doubts of states of matter as well. And yes, guys, please start solving chemical bonding as well over there, because chemical bonding is a huge chapter and huge marks as well. You will get at least 5 questions in your NEET examination. 5, 6, 7 questions, no limit. At least 4 to 5 questions they are gonna ask you in the examination. Okay. So next week we will have structure of atom, and after 2 or 3 days we will have chemical bonding as well. Okay. So we'll follow the sequence: structure of atom, then bonding, then states of matter. Keep solving the questions. Okay. Okay, guys. So let's start with the new chapter. chemical equilibrium. Okay. Chemical equilibrium. Ultimately, guys, equilibrium is divided into the two parts, chemical equilibrium and the ionic equilibrium. Okay. Guys, again, this chapter contains lots of formulas over there, as we have discussed in the structure of atom, as in states of matter as well. Lots of formulas over there, but quite easy these formulas are. Okay. I'll suggest that you can separate the formulas from the chapter as well, okay, for the quick revision from every chapter. Whenever you check out the formulas, just separate those formulas, write it in a new book, or we can say new notebook, and you can just paste them in your study room or in front of your study table. Okay. So chemical equilibrium. So guys, before understanding the equilibrium, first of all, we have to understand the meaning of chemical reactions. Okay. If I ask you, in how many broad parts, see, I'm not going to that micro level, okay, it's on the subcategories. If I ask you that how can you divide, or in how many parts you can divide chemical reactions, that can cover each and every category. Means after that you will get the subcategories, but I'm asking about the two major categories in which we can classify the chemical reactions. Okay. So guys, whenever we talk about the chemical reactions, as I have told you, if someone asks you in how many ways or in how many parts you can classify, so we'll simply say that it can be classified in the two parts. Okay. First one is your irreversible chemical reactions, and second one is your reversible chemical reactions. Okay. So irreversible and reversible, these are the two important reactions are here on which the whole chapters depend. Okay. So let's start one by one. Okay, and we will discuss about these chemical reactions. So guys, first of all, types of chemical reaction. First is your irreversible reaction. Guys, as the name suggests, irreversible means once they have initiated and completed, after that the whatever product is formed over there cannot be converted back into the reactant. Means after the completion of this type of chemical reaction, we cannot convert back them. Okay, these are the what? Irreversible chemical reactions. Now, we can say that a reaction which can proceed only in a single direction, that is reactant can be converted into product, but product cannot be converted into reactant. Okay. Check this one. If I say A plus B is giving you C plus D. This is the representation of the irreversible reaction, okay, where it is saying that A plus B on reaction with each other is forming the C plus D, okay. Now, important points, or we can say characteristics of irreversible reaction. First, proceeds in single direction. Number two, represented by, means this arrow is being used for its representation. Number three, always goes for completion. Always goes for completion. Guys, copy and confirm. Okay, let's move on. Number 4, involves limiting reagent. Number 5, takes place in an open container. For example, all the combustion reaction. Guys, all the combustion reactions, whatever type of combustion reactions are there, once they have burned and they have converted into the ash, or we can say any type of product, you can't reconvert them. Okay. For example, let's say suppose you have 2,000 rupees of note and you burn that note. Okay, just to understand the meaning of this type of chemical reaction. So I'm sure whatever efforts you can make over there, but you can't get that 2,000 rupees back. Is there anyone who can do this? Please let me know the method, that how can we do that. Okay. So please don't do this. This is just an example. Okay. So once they have converted into the ash, that ash cannot be converted back into the reactant over there. Okay. This is the first example of this one. Or we can say precipitated reaction, means precipitation reactions. Once precipitate has formed, you can't reconvert that precipitate into the ionic substances from which it was formed over there. Then reaction of strong acid with strong base. Because they have converted into a salt, and that salt cannot be further treatment with water, or we can say with any substance, can reconvert back to the strong acid and the strong base. Okay, these are some common examples that you should remember for the type of irreversible reactions. There are many more irreversible reactions available to us in the nature, but these are few important ones. Okay, so I hope so it is clear to everyone that what is the meaning of the irreversible reaction. Okay, now Let's start with the reaction on which the whole chapter is going to depend. Okay. The next reaction is reversible reaction. As the name suggests, reversible. Guys, what will happen? Here, once reactant has converted into the product, then product can also be converted back into the reactant. Okay, there is no limitation. See, a reaction which can proceed in both direction, that is forward as well as backward. The catalyst, there can be many examples. Catalyst is just used to provide the path. Okay, catalyst never participate in the chemical reaction, means it won't affect, it won't consumes during the chemical reaction. Okay. Yes, we can use the catalyst in the irreversible reaction as well. Okay, just check out. C plus D. This is forward. Forward means where reactant are getting converted into the product, and this is your backward, where product are getting converted into the reactant. Guys, copy and confirm. Okay. Let's move on to its characteristics. First, proceeds in both directions. Number two, represented by this arrow. Half both-sided arrow. Never goes for completion. Means we can never say this reaction has completed. No role of limiting reagent. Takes place in a closed container. Okay. Let's take an example. N2 plus 3H2 is giving us twice of NH3. Copy. Okay. Now the question is, guys, how we have got the idea of the equilibrium. Obviously, there must be something reason or some scientist over there who first time have observed this phenomena of the equilibrium. Okay. So what happened actually, and how idea of equilibrium has been established. There were scientists, I don't know the name of the scientists, they were actually reacting Fe with water in the open container, and they have got this product. This is in the open container. Okay. And then they were also doing this. This was also in the open container. So they know that if Fe is treated with the H2O, we'll get the Fe3O4 and the 4H2. Okay. Whereas if I treat the Fe3O4 with the H2, I'll get the Fe and the H2O. Okay. So they were doing this reaction in the open container. Then suddenly one of the scientists have attempted, that was random attempt, that what will happen over there if I place Fe and H2O in a closed container. See, in the open container, if I treat Fe with H2O, I'll get the Fe3O4 and the H2, and H2 will goes to the atmosphere. And if I treat that H2 with the Fe3O4, we will get the Fe again with the water. Okay. So scientists had done that. He treated Fe with H2O. This time, not in the open container, but in the closed container. And he got the same results. But with a very interesting thing. He observed that if I place Fe and H2 in a closed container, I can get 4 of these reactants as well as product at the same time. I can get Fe, I can get H2O, I can have Fe3O4, and I can have the H2 as well. Okay. And that time he observed that with the rate by which Fe3O4 and H2 are forming, exactly with the same rate, Fe3O4 and H2 are reacting with each other to form what? Fe and the H2O. Okay. So at that time, they said that it is the state of equilibrium, where the rate of the two sides, forward side and the backward side. Look at this. I can see this is the forward side, where reactant is getting converted into the product, and this one is what? Backward side. They observed that the forward side reaction and the backward side reaction are exactly same. Means with whatever rate reactant is converting into the product, exactly with the same rate, product is getting converted into the reactant. So after that, they have got establishment, or we can say the idea of the equilibrium. Okay. So this is how they have developed the first time the equilibrium state. Okay. So the point that you have to remember for the equilibrium is, for a reversible reaction equilibrium is defined as the point, time or situation at and after which rate of forward reaction becomes equals to what? Rate of backward reaction. One of the most important thing here. And we can say that concentration of reactant and product would be what? Constant. One of the most two important points. Rate of forward reaction will be equal to backward reaction and concentration will be constant. Copy this, guys. Copy this. Done? Senapati, are you there? Okay, what do you want me to explain? The note part. Okay. Note part is nothing but it is the definition of the equilibrium. It is saying that for a reversible reaction, obviously the equilibrium can be achieved only in case of reversible reaction. Okay. So it is saying that the equilibrium is nothing but we can say it is a point or it is a time or it is a situation. You can use any of these words. Okay. And at and after which means at that time or after that time, or we can say at that situation or and after that situation, rate of forward reaction would be equals to what? Rate of backward reaction. Means this is RF and this is what? RB. Okay. If you are saying that it is an equilibrium, then what can you say? That at equilibrium, rate of forward reaction would be equals to what? Rate of backward reaction. R stands for the rate and F stands for the forward. And we can say that at that equilibrium state, concentration of reactant as well as product will be what? Constant. It won't be changed. Once there is an establishment of the equilibrium, at the established time, or we can say at the equilibrium state, forward and backward reaction would be same and concentration part will be constant over there. That's what the note part is saying over there. Get it? See, if I take one example to clarify this, I am saying R is converting into the product. So, okay. So, what can I say at equilibrium? At equilibrium, take it A and B. A and B. This is RF and this is RB. Okay. So, at equilibrium, what can I say? That RF should be equals to RB. And concentration of A should be constant and concentration of B should also be constant. Okay. They can be equal and they cannot be equal. That's a different thing. Okay. But yeah, it must be constant. Whatever value it can have, but it should be constant. Get it now? Okay, let's move on. Guys, first of all, confirm, everyone has to confirm, are you clear up to this point? Do you have any confusion or doubt? You can please ask me. We haven't discussed much, but yes, anything doubt if you have, you can ask me. We have discussed only two things, reversible reaction and the irreversible reaction. Okay. I have explained the difference between these two. Okay. And after that, how equilibrium idea has established, how scientist has got the idea that we can have such situation as well. Okay. Before that, we have only one type of reaction, which is irreversible. After that, we have got such irreversible reactions as well. Okay. Now we are going to start the core section of the equilibrium. Okay. Now let's use the graphical representation. Case 1. Guys, remember those 2 points in the note section. Rate of forward reaction should be equal to rate of backward reaction, and concentration should be constant. Case 1, where I'm taking the rate. I'm plotting the graph. This is the rate, and this is the time. First of all, understand the meaning of this graph. See, first of all, tell me guys, there are two curves. This is curve A and this is curve B. Do not copy this. See, I'll draw these type of graph again and again. So, let us clear the meaning of these graphs. Do not copy this. Just look at the screen. Tell me, between A and B, which one is representing the reactant part and which one is representing the product part? Between A and B. Between A and B, which one is representing the reactant part and which one is representing the product part? A is product. Okay. Okay. No. Let's change the question. Tell me, between A and B, which one is representing the forward reaction and which one is representing the backward reaction? Between A and B, which one is representing the forward reaction and which one is representing the backward reaction? One of them would be forward and one of them will be backward. Okay, A is forward. How do you think that the A is the forward? Exactly, both look like same. Shillong, how can you say that A is the forward? Okay, let me take an example. That's why I was saying do not copy this. Let me take an example. A is converting into B. This is RF and this is RB. Just look at the this chemical reaction. First of all, tell me, before the equilibrium is reached, first of all, I haven't used the word equilibrium till now. Before the equilibrium is reached, tell me, which rate was gradually increasing, forward or backward? At the equilibrium, they both will be equal. At the equilibrium, both will be equal. My question is, before the equilibrium, which rate was constantly increasing and which rate was decreasing between these two? Forward is increasing. Very good. And backward is Backward is decreasing. Wow. Okay. First of all, tell me, this is the state and this is also the state. How can you say that the forward is increasing? According to me, forward should decrease, backward should increase. See, if you are saying that forward is increasing, and obviously forward is increasing, then backward should decrease. If backward is decreased, then how can you say that they can attain the equilibrium? Guys, listen to me. Listen to it very carefully. Try to understand the meaning. I'm saying that if forward is increasing, then simultaneously, see, both the reactions are moving parallelly. Then simultaneously backward should decrease. If backward is gradually decreasing over there, then how can you say that there will be achievement of an equilibrium? No, that will be equal at the state of the equilibrium. That will be equal at the state of the equilibrium. How can you equal the forward and the backward reaction? At which condition you can make them equal? See, RF should be equals to RB. What should be condition to make them equal? If I say that if I decrease the RF and if I increase the RB, then obviously a point will come over there. At that point, they both will become equal. When reaction is actually in the process. When the reaction is in the process. Think about it. Confused? Wait. No. Wait. A and B. I'm saying T equal to 0. At the T equal to 0, we will have what? Only reactant part, na? Guys, look at the screen. Understand this, please. At time T equal to 0, we will have only what? Reactant part. We do not have any product. Okay? So, if we do not have any product, how can you say that product can be converted into the reactant? And guys, those who are talking to each other on the first bench on my left hand side, guys, I have already told you that please do not talk in the class. Okay, let's get back to the point. Guys, try to understand it. At time T equal to 0, we have only the reactant part. No product is there. If there is no product, then how product can be converted into the reactant? Is it possible? I need one person on the system. Just to answer me quickly. On every center. Have you got my question? What I was trying to convey? Okay, very good. So initially, we have only reactant part, no product part. It means no conversion of product into the reactant. So I can say backward reaction should be 0. Rate of the backward reaction should be 0. But forward should be what? Maximum here. Obviously, if one part is minimum, then other part should be what? Maximum. Now, at time T, where some reactant is converted into the product. Means at this time, I'll have A plus B. Still, no attainment of the equilibrium. Okay. Now, obviously, some part of the product is converted into the reactant. Okay. So what can I say? That forward was already maximum. If something is already maximum, you cannot go beyond those limits. So we have to go downside. So what can I say? Forward should decrease. If forward is decreasing, then obviously the other part which is working parallel with it should be what? Increased. If you say at equilibrium part, where again you will have A as well as B, you will say what? Rate of forward should be equals to what? Rate of backward reaction. First of all, tell me, have you got clarification? Have you got something what I have just told you? That initially I have only reactant, so I can say this is the forward only, no backward reaction. So forward should be maximum. Once you have started something conversion of into the product, at that time, product will get converted into the reactant, and we can say that the forward was decreasing and backward was increasing, and that decrease and increase will working simultaneously, and a point will come where they both become the equal, and that is what we call a state of equilibrium. Now have you got that? Okay. What about you, Itanagar, Senapati and Tamilong? And guys, if you have got confusion, you can please ask me. Now tell me, in this graph, which one is representing the rate of forward reaction, which one is representing the rate of backward reaction? Before that, guys, copy this one as well. Copy this one as well. For much more clarification, just copy this. Copy and confirm. And you can say this is the dynamic equilibrium, not static. You're talking about the graph or about this reaction? Graph. Oh yeah, let's check out the graph. Okay, you have copied that. Just look at this. See, between A and B, so A would represents the backward part because it was increasing, and this one will be forward part because it is decreasing. What did you say? That B will be forward and A will be backward. Absolutely right. Guys, I hope so you have got this time. Got it? Okay. Now here, at this point, the rate becomes constant. Okay. First of all, tell me, can this graph represent the equilibrium? Okay, just after the graph. First of all, guys, tell me, can this graph represent the equilibrium state? No. Why? Look at the reaction. Is RF and RB are equal, or RF and RB are constant at time t or after time t? Means this is a question for you. My answer is no. According to me, it shouldn't represent the equilibrium. My question is, after time t, what is the graph representing? RF equals to RB, or RF and RB are constant? Will you say something? Guys, have you got my question? I'm saying after time t, what are they representing? RF equals to RB, or RF and RB are constant? Yes, they are constant, not equal. Okay? Those who haven't got this even, they can do like this. Just draw a line here. Let's say suppose this is point 1 and this is point 2. Obviously point 1 and 2 are not equal. So rates shouldn't be equal. Okay? So for the state of equilibrium, RF and RB should be equal, not constant. Means they can be constant, but equal is the primary condition over there. Okay? So it won't represent the equilibrium. Got it? Confirm it to guys. Confirm it to me, guys. Have you got that? Okay, that's cool. So guys, on demand, let's take a break of 5 minutes. I'll see you in the 5 minutes. Okay. Hi guys, welcome back again. Please settle down fast. And mark your attendance, guys. Every center, please mark your attendance. Now. Okay. Okay. Okay, so let's start again, guys. First of all, tell me that are you clear with this concept? And those students who are busy with their typical talks, please be focused in the class. Yes, I'm talking to you guys on the first bench. One is in the green, other one is in the white or gray, don't know. Not visible here clearly, but a green is visible over there. Yes, you. Okay. So guys, I hope so it is clear to everyone. Okay. She just confirmed me, yes, I won't do this, and after that she will start again like this. What? Okay. Okay, so let's get back it, sorry, what I'm saying. Let's start again, okay? So, I hope so it is clear to everyone. Okay, just in the graph, make sure you are looking at the 2 points. Rate of forward direction should be equal to rate of backward direction and concentrations should be constant. Okay? Now I'm giving you the second graph. Now you have to tell me the answer. Oh. This is the rate. This is time. This is your forward reaction. This is your backward reaction. Tell me, is this graph representing the equilibrium? This is the point where rate becomes constant. Tell me, is this representing the equilibrium state? Will you say something? Okay, who has got this answer? Please tell me your name as well. Annie. What about others? What do you think? Balaji, Nitish, Nafi, Priyanka, Emika, Paul, yes. Okay, Paul is also thinking the same. Yeah, I'm asking what do you think? Oh, I was not asking for the name. I know the name. I was asking what do you think? Okay, Kane is also there. Itanagar has got something different answer. Absolutely right. So my dear superstars, I don't know what you have got in the first graph. I told you whenever you got confusion, just draw it like this. This is point 1, this is point 2. Now tell me, is RF equals to RB? Is RF equals to RB? Yes, if they are not equal, then how can you say it is the attainment of the equilibrium? For the equilibrium, either rate should be equal or concentration should be constant. I am discussing the case of the rates. Okay? So as RF is not equal to RB, so no equilibrium. Copy please. Rate is constant again, guys, not equal. We have to make the rate equal. First of all, understand the difference between the equal and the constant. Okay, I'm drawing the next graph. See. This is your RF, this is your RB. Tell me, is this represents the rate of, state of equilibrium? Okay, very good, Itanagar. Shillong, you are saying third time yes. I don't know why. But yeah, this time you have got the correct answer. Yes, because here, look at this. If I look at this point here, RF is equals to RB. That's why this is representing the state of equilibrium. Okay, so congratulations to all of you who has got the correct answer. Okay, let's discuss the case number 2. I hope so this time we will get the correct answer from the beginning. Case 2, this time I'll discuss about the concentrations. Okay, see, this is concentration. And this is time. This is your reactant and this is your product. Okay, check out this point. Now tell me, can this graph represent the equilibrium? Please think about it, then tell me your answer. Don't be so quick to give the wrong answer. Think about it and tell me the correct answer. Guys, now you have taken lots of time. Now you can tell me the answer. What can we answer for this one? This line means it is not changing. It is not changing. Okay? Not changing means the concentration of product and concentration of reactant is not changing. Yes, they are not equal, but reactant concentration is constant after that point, and product is also constant. Now we have shifted to the concentration part. If the concentration becomes constant, then yes, state of equilibrium. Got it? Guys, in the case of the concentration, just check whether it is constant or not. Okay, nothing else. Copy this one. I'm drawing the next graph with an expectation that this time I'll get the correct answer. And my dear student who is in the red on my right hand side, dear, are you sleeping in the class? Hey, look at here. See, someone is saying hi to you. Good morning. Yes, I'm talking to you. Yeah, that's better. Okay, I'm giving you the next question. Tell me, can they represent the equilibrium or not? Just in case of concentration, just check out the reactant and product are constant or not. Okay? Concentration, time. Reactant, product. Reactant, product. Tell me, are these graphs representing the state of equilibrium? Might be one is representing, might be both are representing, and might be none of these are representing the state of equilibrium. Tell me, what can be answer for this one? Guys, have you done that? Copy please and confirm this answer. Okay. Are you sure, Shillong, this time? Itanagar, just check it once. Who has got this answer at the Shillong Center? Yes. Kirpeng has got the answer. Only one in the class. Yes, absolutely right. Here, concentration of R, look at this, is constant, constant. So it is equilibrium. Absolutely, it is equilibrium. Look at this. This is R and this is P. Again, they are equal, fine. But they are constant as well, guys. They are constant as well. So I have to check out the constant only. Okay? So if constant, then absolutely they can represent the state of equilibrium. Okay, guys, have you understand the concept? Okay, let's move on. So guys, such graphs are quite important for the examination point of view. Okay, now let's start with the type of equilibrium. Physical equilibrium means where change in phase. Okay, Itanagar, do you have any question? They both are representing the state of equilibrium. Do you have any other question? If yes, you can ask me. Guys, physical equilibrium means where the change in phase will takes place. Okay, the change in phase will takes place, like solid to liquid, liquid to gas, gas to solid, and so on. Okay, means these are the examples of the physical equilibrium. Okay, where physical state will change over there. Okay, so we can say that equilibrium established for physical. Okay, it's okay, dear. Itanaga. Physical process that is phase transformations. Phase transformation and allotropic changes. No problem, no problem. And allotropic changes. Okay. For example, H2O solid is in equilibrium with the H2O liquid. Like H2O liquid is in equilibrium with the H2O vapors, which is a gas form. Carbon diamond form is in equilibrium with the carbon graphite form. Okay. Next is your chemical equilibrium. Okay. Here equilibrium will establish for a chemical reaction over there. Okay. So we can say that equilibrium established for chemical reaction. For example, N2 plus 3H2 is giving you what? Twice of NH3. H2 plus I2 is giving you what? Twice of HI. Copy, guys, and confirm. Guys, copied that? Okay. Shillong net speed is quite slow, so I cannot see your actions. You know what? Yesterday, I was thinking that I should say it to you that you guys are one of the sweetest person that I have ever met till now in my life. But after today, I think so that I should change this statement. I should think about it again before saying this. Yeah. Oh, let's continue with the topic. Okay, not finished. Yes, just copy. You know what? You know what? Why I was saying this? I should change my mind now, because I can see some person are just doing whatever I'm telling them to do. They're not doing that. I said, please stop talking, stay focused in the class. They're still talking to each other, don't know what. See, whenever I'll come to Shillong, I'll ask them what exactly they talk in the class. But yes, guys, that's true, actually. You guys are really sweet, okay, that I have ever met. Up to now, one of the sweetest person, okay. I really enjoy this class. But yeah, unfortunately, due to the lack of the syllabus, we can't talk a lot, okay. So it's fine. Dear, have you copied that? Who haven't copied yet? Okay. Okay, so guys, let's start again. Okay, let's continue with the characteristics of the equilibrium. Okay. Characteristics. First, and before this, guys, just confirm it to me. Have you got the points that I have discussed with you till now? Is everyone understood that? My dear student, on my right hand side in the red, look at here, look at here. Yes. Have you got that? Why you remove your cap whenever I talk to you? And before that, are you in the state of the sleeping while putting your hood over your head? Oh, thank you. Now you can keep your hood over your head again. Okay. Might be there is winter as well. Okay. Okay. You can relax now then. If you are having the headache, you can relax. Okay. So guys, let's start with the characteristics. Okay. And please guys, revise these concepts again at your home. Okay. See, equilibrium has got very deep concepts over there. Okay. Wow, too cold. Here it is about 30 degrees. See, here in Delhi it is 26 degree. And I am only in a shirt. Wow. Oh, 13. Now you have rights to put your hood over your head. Now it's fine. Okay. What I was saying that please revise it again at your home as well. Okay. Very deep concepts are there. So characteristics, let's check out. Equilibrium can be established any direction. Means backward as well as forward. Means from product side as well as, yes, from product side as well and reactant side as well. Okay. Number 2. At equilibrium, rate of forward reaction would be equals to rate of backward reaction. Number 3. Equilibrium is dynamic in nature. Number 4. There is no change, means these properties will become constant. No further change will be there. No further change will be observed over there. In any of the measurable property, that is pressure, volume, concentration, temperature, mass, moles, etc. After attainment of equilibrium. Attainment of equilibrium. Number 5. There is no effect of catalyst at equilibrium. See, if equilibrium is achieved, then no effect would be there of the catalyst. Okay. But yes, to attainment of the equilibrium, we need catalyst. It can only after alter time required for attainment of equilibrium. Okay. And important point, at equilibrium point, delta G would be 0. You will see this statement many a time. Copied? Guys, have you copied that? G is the Gibbs free energy. G is your Gibbs free energy. We'll discuss about it in the thermodynamics section. Gibbs free energy. Okay. Now, law of mass action. First of all, let's write its statement. After that, I'll make you understand that what does it mean. Okay, just copy this. It states that under given set of condition, the rate of reaction is directly proportional to product. Guys, first of all, understand this product is not the product of the reaction. This is the mathematical. Means in the mathematics we use plus, minus, add, subtract. What I say? Plus, no, add, subtract, not add, subtract. Multiply and divide. So this product means multiply. Okay? Don't confuse with that. This is representing the multiplication. Proportional to product of concentration of reacting species. Okay? This is a law of mass action. It says that simply under a particular set of conditions of temperature and pressure and some other factors as well. So, if I talk about the rate of reaction, then rate of reaction would be proportional to the concentration of reacting species. If you remember, guys, we have already discussed about the rate law, and the rate law was exactly defined in this manner. That rate of reaction is proportional to the concentration of reacting species. Do you remember that? This is the same. Okay? So now, let's understand it a little bit more. I am saying this is a chemical reaction giving C plus D. This is forward. This is your backward. See, if I am saying rate of forward reaction, for the forward reaction, A and B are the reactants. So I can say concentration of A and concentration of B. Okay. I have removed the proportionality sign and I'll simply say it is what? KF. A and B. If I say backward reaction, tell me. Okay, I'll tell you. For the backward reaction, obviously C and D would become what? Reactants for the backward reaction. C and D will behave as a reactant. So I'll say this is equals to what? KB, C and D. Guys, look at the screen. Do not copy it. Just understand the meaning of this one. Okay. Now, when we say equilibrium state, at equilibrium state, we can say that RF should be equals to what? RB. We have already studied about it. Okay. So I'm just putting these values equal. And on putting these values equal, see, what can I say? KF, A and B is equals to what? KB, C and D. Okay. So I'm just simplifying it, and on simplifying it, I can say KF upon KB should be equals to what? Concentration of C, concentration of D upon concentration of A and B. Okay. Guys, this ratio of KF and KB is known as what? Equilibrium constant. Okay. This is known as what? Equilibrium constant, and this is our resulting final result. Now, the K equilibrium can be of two types. I can write it here. It can be of, okay, I'll write it on the next one. Guys, first of all, confirm me. Have you got clarified with this one? Copy it and just let me know that are you clear with this one? Okay, very good. I can see only one hand. Okay, now many hands, slowly. Why you have changed your seats? Nafi is sitting on the right hand side, who always sits on the wall side, and I guess don't know who is on the wall side. Might be Priyanka. Even Amika has also changed her seat. And the two students who just sit at the last, I think they are not present in the class today. Wow. And I think Balajit and Paul is on their same seat. They haven't changed their seat. Okay guys, copy it quickly. Just confirm it to me. Done? Okay. Temilong, Senapati, Itanagar, guys, have you copied that? Okay. The important part. It can change only with the temperature. Guys, remember, equilibrium constant can only be changed in one condition of the temperature, otherwise you can't change it. Okay? And remember, this is a very important part where you can get the questions. Now, I was saying something about the K equilibrium. So, K equilibrium can be of two types, Kc and Kp. Okay? C stands for the concentration and P stands for the pressure. Okay? We will subdivide the Kc and Kp further. Okay? So, to write the K equilibrium, what you have to do, simply write the concentrations of the product in the numerator part and concentration of the product, sorry, make it reverse. To write the K equilibrium, just write the concentration of products on the numerator part and reactants on the denominator part. Look at this, the reaction was saying A plus B is giving you C plus D. Now, if I would like to write the K equilibrium, I'll simply write concentration of product, which is C and D, upon concentration of reactant. Okay? Let's take another example. Let's say suppose I have to write K equilibrium for this one. 2A plus B is giving us C plus D. Okay? So if I would like to write the K equilibrium, see, I'm not writing the Kc and Kp, I'll write it later on. Okay? So I'll write C, D upon A. Guys, remember one thing, that whatever coefficient is given there, it will become the power. Coefficient will become the power. See, this is how we can write the K equilibrium. Got it? Guys, have you got that? Just copy this. So guys, about Kc and Kp we'll discuss in the next class. Okay, so by the time you can revise it. And yes, in the next week we will have a doubts of atomic structure as well, and just after that I'll take the doubts of the chemical bonding. Chemical bonding from the sheets that I have shared with you. Okay, the previous year's questions. And still, if you need some more questions, you can please ask me in the group. For the more questions, I can definitely share the new questions with you. Okay. So guys, till then, take care. Bye bye. Stay healthy. See you next time.